only loosely.
Now we're good.
Okay, so 6-3, here we go. 6-3 is only loosely connected to anything we've been doing. It's slightly connected to 6-2 when we talked about inverses, because they're going to tell you that the inverse of E stuff is natural logarithm stuff, which the button on the calculator for that and the punctuation on the board for that is LN. So the L stands for logarithm, the N stands for natural. We've done some logarithms before, but it's been a while, so this is largely going to be a logarithm review, I think, today, but with a little bit of calculus mixed in as well. But just like adding and subtracting undo each other, E's with powers and LNs undo each other. So if I take e to a power, and that power has a logarithm with an x, the e and the logarithm are opposites. And what's left standing after they opposite out each other would just be an x. Likewise, if we have a logarithm problem and then e is in it and going to a power, the logarithm of e to a power, the logarithm and the e nullify each other, and you're just left with x. We can only do that if the e and the ln are like next door neighbors, essentially. Like e's power has logarithm, logarithm has an e. They need to be directly side by side without other stuff interfering, but they nullify each other. And then there's examples 1, 2, and 3 from the book, so I'm just going to sit down and find those and just steal their example, and we'll look through them. So if you want to join me, I'm working from page 362. So 362, example 1 has for part A an e next to a logarithm, and they just bump each other off, and after the equals they wrote down the other stuff. So that's a lot like what we just did on the board. B is not ready to roll right now. Why is B not ready to roll right now?
Did that count as being next to each other or no?
No.
Okay.
So like the 3 is in the way. The e and the logarithm aren't like directly next to each other. So what they had to do on B is figure out a way to like resolve this. So what's happening here, powers and logarithms are opposites. So last time I think we did, or maybe it was 2 times ago, we did a bunch of power rules. Like if you're multiplying powers, it makes the powers add. If you're dividing powers, it makes the powers subtract. This has some multiplying powers. What makes you multiply powers is if powers go to other powers. So what they're going to do on B is rewrite this so that the 1 power is going to another power. The 3 was the number that's kind of like in the wrong spot from our point of view. So they nudged the 3 outside of a set of parentheses. So the multiplication of powers, they changed into a power to a different power problem where the 3 got relocated. Then in the parentheses, the e and the ln can bump each other off to just make it 2. The 2 is the full value of those parentheses. Then you could worry about the cube. 2 cubed is 8. Anybody want me to rewind that? Okay, C has a similar issue. C, the e and the ln are not directly interacting with each other. That x is in the way. So what they do is they try to figure out a way using some powers rules from before to rework this problem. So what made powers add was previous experience with multiplications. So what they did on C, they saw some adding powers and they thought, we'll change the way this looks, we'll make some multiplication happen. So they did an e to the x multiplying an e to the ln2, and that would cause that addition to happen. The e to the x, they just left it be, they're just stuck. But the e with the ln can reduce down to just being a 2. And then their preference is to write the 2 out in front. That all those coefficients you've dealt with in your algebra life, you've nudged them a lot to the front. D, they do a similar rework. The e is not immediately in contact with the ln. That negative's in the way. So they had a flashback to the fact that negative powers flip things. So they took that negative power away and they flipped it. 1 on top of, and now it has a positive power. And now the e is next to the ln, where they can knock each other off and just leave an x. So that's D. A to D were like the e was the central figure. Question on that? Then e to h go inside out, where that logarithm will be the central figure. So on e, the logarithm's next to the e, they just wrote down a 3. On f, the logarithm's not next to the e, the square root's in the way, so they rewrote the square root as a half power to get that out of the way. And then the answer would be a half after the ln and the e knock each other off. G, the ln is next to the e, so just write down the power. On h, the ln's next to the e, just write the power. So the name of the game there is ln's, e's, they're inverses, they're opposites, they'll bump each other off. Anything there want rewound? Example 2, they're using that concept to solve an equation. So on example 2, if they want to solve an equation, you know, we're back to the 7th grade and equations like a scale. Whatever you do to one side, you do to the other. You're doing your opposites, all that business. So for example 2, if you want to get the y alone, what you need to do is get rid of the logarithm. What gets rid of logarithms is taking e to a power. So on the left, they took e to a power and they copied that whole side. On the right, they took e to the power and they copied that whole side as the power. And then on the left, the e bumps off the ln to just leave you the y you wanted to solve for. So y would equal e to a power. So if you have to solve an equation with a logarithm, the answer is going to have e's to powers. Conversely, on example 3, if the equation has e's to powers, your answer is going to have a logarithm. So what they're doing here on example 3, if the goal is to solve for k, they want the e out of there. So on the left, they did a logarithm of the whole side. And on the right, they have to do a logarithm of the whole side. On the left, the logarithm kills the e to leave you 2k. On the right, the logarithm of 10 is just a number. Okay, like the square root of 10 is just a number. It's not a number you know, but it's a number your calculator could give you access to if you wanted it. To get the k alone, they would then divide by 2. So if it were my paper personally, I'd probably have written logarithm of 10 divided by 2. They chose to write instead of a divide by 2, they put a half in front of the logarithm. I'm good with this. I'm good with this. I'd rather not grab the calculator and punch stuff in, because then I'd have to round. But if you do grab the calculator and punch stuff in and round, they did that. They tell you it's about 1.15. One thing you can't do is, even though 10 divided 2 is 5, logarithm of 10 is not touchable. Kind of like if I told you that the square root of 10 is dividing 2, you're maybe tempted to divide those numbers, but you can't. Roots can only divide other roots. Regular numbers can only divide regular numbers. Logarithms and roots are similar in that they're like untouchable to the normal number world unless you're going to break out your calculator and round. Question about that? Yeah.
Can you re-explain example 2?
Example 2, they want to get rid of the ln, so they took e to a power, because e's to powers is what kill ln's. So on the left, e went to a power and they copied that whole side. On the right, e went to a power, they copied that whole side. The left side simplifies because e's next to ln, so it just leaves you the y after they knock each other off. And on the right, you're just kind of stuck e to that power. That's just the answer. Okay. Anything else? Example 1, 2, 3, rewind. And I'll stand back up. Again, I don't think we did with your group logarithms in Algebra 2. Some groups do logarithms in Algebra 2, but your group finished Algebra 2 in quarantine at home for like the 4 months home from 2020 COVID issues. So, but other people who view this video in the future might have had some Algebra 2 logarithm experience, but I don't think you guys did. Everybody should have some trig logarithm experience, which you definitely would have had last year. So there's 4 basic super important properties of logarithms. One is that if I give you a logarithm problem with multiplying, you can turn that into 2 mini logarithm problems. Do you remember what we do? We will add, because this is just the opposite of powers. Okay, when we add power, or when we multiply powers, it makes us add the powers. That's the same idea, but like in rewind now. Okay, logarithms powers are joined at the hip. So if I give you 1 logarithm problem with division, you can make 2 mini logarithm problems but division would make you subtract. If I give you something that's upside down, you can turn it right side up. What kind of powers do that flippage for us? Negative powers do flippage when we want it to. And then this is the most often done logarithm trick, I feel like, is if we have a logarithm problem that has powers, you can basically just slide that power to the front. It almost feels like you're doing a derivative, like we've done derivatives that way a lot by sliding those powers to multiply to the front. It has nothing to do with derivatives, it just has the same feel to it. But powers can just slide to the front. That's like 4 super important abilities to deal with logarithms. And it works forward and backward. Like if I said logarithm of 2 plus logarithm of 3, what would logarithm 2 plus logarithm 3 make? Logarithm 6. So it's a two-way street. There's examples 4 and 5, so now I'll sit down and we'll look at those. Hey, they stole my problem. It's in my memory banks, I guess. I couldn't resist myself. So for like this example 4, there's not really directions to guide as to why they're doing this. They're just showing you how things could be done. So if you're like, how did they know to do that? Well, they're just showing off essentially. But for A, instead of logarithm of 6, they said, 6 is 2 times 3. So I could make 6 into a 2 times 3 kind of problem, and then show off my logarithm knowledge. Multiplying makes us F. Logarithm 2 plus logarithm 3. I can't say any of those is like better or worse. It's just they're equal, and they can be one change to another. For B, they have logarithm subtracting, so they make one logarithm problem and they're dividing it. And then if you'd rather have a decimal than have a fraction by actually dividing it, those are all, to me, about comparably good. I don't think, again, that anything's better than anything else. They're just showing off. Example 4C, they have a 1/8. They turned that into an 8, and they threw a negative in the front. That seems like a fair trade. And then they thought, hey, wait a minute, 8, I could rewrite 8. 8 is 2 cubed. And then I could slide that power to the front. Again, I'm not sure which answer really is like the best answer, but they're just showing you ways we can trade these. 5A, same kind of thing. They have 2 logs that are adding, so they made 1 log and they multiplied that stuff. B, they had 1 log that was dividing, so they made 2 logs and it was subtracting that stuff. For C, they don't really like secant. Secant is cosine flipped, so they flipped it, and that created a negative in the long run. D, cube roots is the same as 1/3 powers, and then they slid that 1/3 to the front. Those are just some decent tricks. Question about that? Then here's debatably the funniest box in the whole book. A little bit of history is in this book sometimes from time to time. Sometimes I read these books, these boxes. This one I read every year because I find it entertaining. It has a surprising finish. But this is sort of how logarithms were used in the days before calculators. So they said in the late 1500s, there's a Scottish baron named John Napier who invented this device, this math device called a logarithm. It simplified arithmetic by replacing multiplication by addition. The equation that accomplished this was logarithm of ax equals log of a plus log of x. So in the days before calculators, if they wanted to multiply 2 positive numbers, they would look up their logarithms in a table, add the logarithms together, find the sum somewhere else in the body of the table, and then read the table backward to find the product. So, like if we had 4,387 times 124. Okay, what they would do is they had this table of logarithms where they would look this number up, and that would be 3 point something. Because like scientific notation, it's moved over 3 spots kind of stuff. This would then have to be 2 point something. And I don't have a table, so I can't look these up. But we have 3 point something plus 2 point something. They'd add those up to get 5 point something. Somewhere later in the table, leaf through it, the table would be like a book. Leaf through the table, somewhere later in the table, you'd have 5 point something, you'd find it, and you could figure out that you had a multiplication answer. That was like their shortcut to multiply. You'd probably rather just multiply it by hand, because that's not that big. Nobody would want to multiply that. But it wouldn't be that bad to look up something in a table, and this would be like 6 and some change. This one would be 5 and some change. You keep leafing through your table until you got 11 and some change, and you could link that to whatever that product would have been. Days before calculators, 1500s, they were pretty pleased with themselves. Having the table was the key, of course. And Napier spent the last 20 years of his life working on a table he never finished, while the astronomer Tycho Brahe, or Bray, depending on your point of view on his name, waited in vain for the information he needed to speed his calculations. You might vaguely remember from physics, Tycho observed the heavens. Tycho wanted to do math on things. Tycho didn't get the math done, but Tycho's assistant was Kepler. And then Kepler, after Tycho dies, Kepler did the math, and Kepler came up with all these laws of planetary motion, like the paths of the planets were ellipses and different things like that. Kepler did the math after Tycho died, because Tycho couldn't do the math because he's waiting on Napier. Like, Napier's the hang-up on this project. Like, hey, Napier, get me this table, and he didn't have it. So, you know, they're probably trying to multiply numbers bigger than this somehow, and they need an 11 point something number, and the table stopped at like 10. So they just like kind of build this table, and in 20 years it didn't get done. But the table got completed after Napier's death and after Tycho's death by Napier's friend Henry Briggs in London, and then I guess Tycho got to do his math. Base 10 logarithms subsequently became known as Briggs logarithms. What else? Poor Napier invented the whole thing, dies, and then Briggs finishes it and gets it named after him. Some books on navigation still refer to them this way. So that's where logarithms are from historically. And then here's a ridiculous sentence that just is not where I was expecting this to turn. Napier also invented an artillery piece that could kill a cow a mile away. Horrified by the weapon's accuracy, he stopped production and suppressed the cannon's design. If you were in the 1500s and you had a cannon that could accurately hit a cow a mile away, I'm convinced Napier could have ruled the earth. It would be like strapping a cannon here on the roof of our building and hitting like a turnpike booth. The turnpike is about a mile away from here. Glenn's is about a mile away from here. Imagine setting up a cow at Glenn's in the parking lot, and we've got our cannon here in Cheswick, and you could hit that cow. That's like pretty unbelievable now, let alone in the 1500s. So I don't know if he should have really hidden that weapon. He should have maybe conducted a demonstration, and then he could have ruled the earth if he had a cannon that could hit things the size of a cow a mile away. That's pretty wild and crazy, but John Napier, my friends. The main thing in this lesson that will be lasting for calculus, this stuff is like super good knowledge for math team stuff. Like, math team likes to work through those logarithms. So anything that has logarithm stuff, it usually works through these, and that's a little rusty for us sometimes. But the main thing that wants to be on your calculus card is derivatives of logarithms. So if we do derivatives of natural logarithms, they're always going to make fractions. You're always going to copy the original thing to the bottom of that fraction. And then on the top, we're going to do the derivative of the thing we put on the bottom. And that's going to be a calculus superstar idea. So if I want the derivative of this logarithm, as soon as I see derivative of logarithm, I just make a fraction bar downstairs. Copy who? X squared plus 3 to the bottom. Above it, 2x. Then you move on with your life. If these all had X's, you could have dropped an X. If these all had numbers divisible by something, we could divide those all by something, but it doesn't usually pan out that way. So this, I see derivative of logarithm, I just go fraction bar. I like to do the bottom first. Top. And in most cases, you're done. In this case, you might sense something afoot. Your algebra spidey senses should be tingling.
Okay.
Factor, top you can take out getting
X plus 3.
and the bottom,
X plus 3 squared.
it is x plus 3 squared. So best answer would be
2 over X plus 3.
2 over a single x plus 3. This one, I see derivative, I see logarithm, I just write fraction bar out of instinct. Bottom,
Sine X.
and then is the derivative of sine negative or positive cosine? Is positive cosine. And then your trig spidey senses should be tingling. That is cotangent x. If they want to be mean, they could throw here like an x to the 5th. And now what did they just make you do?
Just do the
They forced an old thing back upon us from like chapter 3. Not the chain rule, product rule. We copy the first times that derivative plus copy the second, and the derivative of this would make
5x to the 4.
5x to the 4th. So we get this thing with an extra x to the 5th on top would get us 2x to the 6th plus like a whole other thing. I don't know if they'll do that or not, but they could. I don't think they'll do quotient rule on these. If they do, that's kind of mean because you already have a fraction. And so if they did quotient rules, you'd go to the bottom times the derivative of the top, which is a fraction, minus the top times the derivative of the bottom, which isn't bad, but then that's all over the bottom squared, and you've got fractions and fractions. And I don't think they do that. I don't have a great recollection of that happening to me in my life. So I don't think you'll see that rule. But one never knows. Let's take a look at homework page. I think we're going to be here, remembering right, there's like 4 days maybe of 6.3. So this homework goes to 370. Today is going to go odds to 40. So the first group is pretty much just playing around with the properties. Up to 18, it's a lot of stuff like we were doing when we were looking up the book examples, 1, 2, 3, 4, 5. Those book examples we kind of read through. That's kind of guiding you on the 1 to 18 stuff. Then from 19 to 40, what takes over is the derivative concept, the superstar, make sure it's on your card idea. And there is a little bit of a medium bit of product rule and a little bit of quotient rule. There's no quotient rule as ridiculous as the one that I just like described to you there that we would have had, but there is some quotient rule, product rule stuff going on. We usually take 2 days to poke through this. So there's usually an odd day, and then people usually will say they'll find some comfort in doing the evens just to get a little more solid practice out of this. Then there's another day where we'll be on this doing 41 to 52 as a separate lesson, and then we keep working from 53 to 75. That's like a whole other lesson. So there's like 3 lessons off of this, and usually 4 to 5 days worth of homework when all is said and done. That's all we got for today.